Welcome to lecture number 18 of PH 4105, Advanced Mathematical Physics. In the last lecture, we started discussing about covectors and differential forms. We are going to continue with that discussion in this lecture. But first, this topic may be quite new to a few of you. Let me quickly recapitulate whatever we discussed in the last lecture. First, covectors. What are covectors? They are linear maps from TPM, the tangent plane to a manifold M at the point P, to the set of real numbers. And a very important example of covectors that we discussed was the differential of a smooth function f at the point P. DFP was defined to be a map which would act on tangent vectors at the point P, in particular acting on VP. It would give us a real number, and that real number was defined to be the result of VP acting on F. Now, since covectors are dual maps, and as we discussed in the last lecture, this is a standard result in linear algebra, that dual maps form a vector space. So instead of all covectors at a point P, TP star M is a vector space in its own right. It actually is an n-dimensional vector space. And if you collect all the TP star M's together and form a union out of them, what you get is the cotangent bundle. This is an exact analog of what we have for vectors. If you take all the tangent planes of a manifold together and collect them together in a union, what you get is a tangent bundle. This is a dual, so to speak, of that. Now, just like you get vector fields which are maps from the manifold to the tangent bundle, but special kind of maps where every point in the manifold is mapped to a vector stuck to that particular point, you have covector fields, which assigns to every point P of M a covector which is stuck to that particular point. That is a covector which is a member of TP star M. Now we can talk about the action of a covector field on a vector field, and the result is a function. Basically, a covector field alpha maps vector fields to functions by the following rule. Alpha acts on a vector field capital X to give you alpha of X, where alpha of X is a function whose value at the point P of the manifold is defined to be the result of alpha P acting on XP. And you define a covector field to be smooth if whenever it acts on a smooth vector field, the resulting function is a smooth function. Now these smooth covector fields are very, very important. They have a special name. They are called differential forms or one forms. And the set of all one forms, which we denote by lambda 1m, was shown to be a module under the ring of all smooth functions. Now, one differential form that we actually met in the last lecture happens to be a very important one form. Given any function f which belongs to C infinity m, the covector field df, the differential of f, is defined simply by saying that to every point P of the manifold, it assigns the covector dfp, the differential of the function f at the point P. We had shown in the last lecture that this actually is a smooth map. This actually is a smooth covector field. And this will turn out to be one of our most important examples of one forms. Now, something that will play an important role, especially in our later discussions on differential forms, is this operator D that you can see here. What does D do? It acts on a function, a smooth function, a member of C infinity M, to produce a lambda 1m member, that is, a differential form, or a one form. F gets mapped by D onto df. Now this D operator has certain properties. For example, if you take a linear combination of two functions, smooth functions, f and g, that is, you multiply them by two real numbers a and b and add the results together, and then apply d on that. This is something which we expect to be linear, but we need to check it out from the definition. Note that we already have this simple formula that for every smooth vector field x, df acting on capital X gives us x acting on f. So let us just choose a particular capital X from the set of smooth vector fields and let us apply d of af plus bg on that. By definition, that is the same as x acting on af plus bg, and as we have discussed earlier in the case when we were talking about vector fields, this is easily shown to be the same as a times x acting on f plus b times x acting on g. Now, xf is the same as df acting on x. xg is the same as dg acting on x. So, this, by the definition of multiplication of differentials or covector fields by numbers and their addition, this result is the same as ADF plus BDG acting on X. Now what I said right now may sound like a bit of a pompous way of saying something very obvious, but you have to realize that addition of covector fields is in itself a definition, and we actually have made use of that definition to go from this step to here. This is one property that we are seeing now for D. Acting on any smooth vector field X, D of AF plus BG produces exactly the same result as ADF plus BDG does on the same vector field X. And since this works for all X, this is an equality of the covector fields themselves. D of AF plus BG must be ADF plus BDG. In other words, D, this operator which maps functions into differential forms, is a linear operator. Now this result should seem very obvious to anybody who has studied a bit of calculus, but you should realize that this D is actually something which is acting in a slightly different setting from the D in calculus on Rn. However, the beauty of all this is the same results ultimately work out. Now our next result about the D operator will be even more reminiscent perhaps of your calculus days. This involves the action of D on a product of two functions f and g. And once again what we will do is apply dfg on x. And that's the same as x acting on fg. And we had already discussed before when we talked about vector fields that a vector field acts like a derivative on a product of functions. So x acting on fg is f times xg plus g times xf. Now we can simply rewrite the xg here as dg acting on x and xf here as df acting on x, and the two together will give you the result that this is fdg plus gdf acting on x. And since this works for all smooth vector fields capital X, d of fg is fdg plus gdf. This, of course, as I have said before, should remind you very much of the differential of a product that you have studied in high school calculus. We will next turn to the issue of how to describe covectors, covector fields, and differential forms in terms of coordinates. Now let me remind you that the set of covectors form a dual space to the set of tangent vectors, and we have already discussed in the last lecture that the dual space V star of any n-dimensional linear vector space V is also n-dimensional, and what is also quite important is that if you are given a basis V1, V2 up to Vn of V, you can use it to construct a basis of V star, something which we call the reciprocal basis. Those of you who have studied a bit of condensed matter physics would definitely realize that the reciprocal basis vectors, when we talk about lattices, essentially are the same thing as these reciprocal basis vectors. Anyway, what we have is a set of n covectors, n elements taken from V star, phi 1 up to phi n, where we define the phi i's by demanding that phi I acts on Vj to give you delta ij. That is, gives you 1 when j is equal to I and 0 whenever j is not equal to I. With this background, let us go into talking about the coordinate picture for covectors. If u, phi is a chart on our manifold M with corresponding coordinate functions x1, x2 up to xn, then the coordinate functions will have differentials dxi at a point P, dxi P, which will act in the following manner. Acting on del xj at P, the tangent vectors to coordinate curves, you will get the following. From the definition of a differential of a function acting on a vector, what we get is the result is the same as del xjp acting on the function xi, and as we have seen several times before and should be sort of obvious from the notation, this is delta ij. So, quite clearly, given the fact that the del xjp's form a basis of the tangent plane TPM when j runs from 1 to n, the dxips actually provide us with a basis for the dual space TP star M. So this gives us one very convenient basis to use in TP star M. Of course, as is always the case with linear vector spaces, the choice of a basis is not unique. There are many other possible choices. However, this particular choice sits in very nicely with the coordinate system. Just take the coordinate functions and their differentials at a point P taken together is going to form a basis. Now, if alpha p is any covector in TP star M, the value of alpha p acting on Vp can be rewritten in this form, where Vp is any tangent vector. Note that any tangent vector at the point P can be expanded in terms of the basis vectors del xip. Not only that, we know that the coefficients that will sit in front of the del xips in this expansion are nothing but the results of Vp acting on the coordinate functions. Now, because alpha p is linear and these Vp xi's are just numbers and this is just a linear combination, this is going to be the same as Vp xi multiplied by alpha p acting on del xip. Note that alpha p acting on del xips are just n numbers. Now, we have just rewritten that here with a slight twist. We have just shifted the order of these two terms, and we have recognized that Vp xi is by definition of dxip the same as dxip acting on Vp. And now we invoke our definition of how covectors are added to say that this thing here defines a covector. Alpha p del xip, this is the ith number, times dxip, a covector, and you're adding all of these together. So this overall thing is a covector which is acting on Vp to produce this result. So now, what have we ended up with? We have ended up with the statement that alpha p, any member of TP star M, acts on Vp to give you something which is given by this covector acting on Vp. Now, since this works for all Vp in TPM, the two expressions that we have, this one and this one, must be exactly the same. This, of course, is nothing but the statement that you can expand alpha p in terms of dx1p, dx2p up to dxnp. which is of course just the statement that this forms a basis. But what is important is that this also tells us exactly what the coefficients of the expansion are going to be. Just like the expansion coefficients for a vector Vp, when you are using the coordinate basis, the basis provided by the tangent vectors to coordinate curves, is simply given by the vector Vp acting on the function xi, the ith coordinate function. Here, the coefficient for alpha p of the basis vector dxip is simply given by alpha p acting on the ith coordinate basis vector del xip. So the numbers which are sitting in the coefficients automatically come out of this result. Now, what if alpha is a covector field rather than a covector? Then alpha at a point P is nothing but this, which we denote by alpha P, but it's something which belongs to Tp star M. So which of course can be expanded in exactly this fashion. So alpha at a point P is alpha of P, that is this alpha P, this thing here, acting on del xip, dxip. Now, notice that this result is the same as alpha acting on del xi at the point P. This exactly is how the action of a covector field on a vector field is defined. You essentially take the value of alpha at that point and del xi at the point and apply one on the other, which is what has been done on this side. And what is dxip? By the definition of differential of a function, dfp is nothing but the value of df at the point P. So this is the differential of the ith coordinate at the point P. And when you combine these together, this is nothing but alpha del xi, which, remember, is a covector field acting on a vector field. It's a function times dxi, the coordinate differential, at the point P. Since this P can be any point, what we have is a covector field can be expanded out in terms of the coordinate differentials in this manner. Alpha is alpha acting on del xi, dxi, and alpha acting on del xi are a bunch of n functions which we denote by alpha I. So every alpha can be written down as alpha I dxi, and the functions alpha I are nothing but the result of the covector field acting on the ith basis vector. Let me stress one thing at this point. We have been talking about covector fields as if they were defined all over the manifold M. However, that may or may not be the case. Sometimes the covector field may be defined all over a manifold, or sometimes it may be only defined locally over some open neighborhood of the manifold. Now, be that as it may, this particular expansion, alpha I dxi for alpha, of course works only as long as we are within the domain U of the coordinate chart. In fact, if alpha is not defined globally, we have to be even more careful. This expansion alpha I dxi is defined only within the intersection of U and the domain of definition of the map alpha. Let us now illustrate this result for the most obvious covector field that we know, the differential of a differentiable function f. Note that according to this, df must be the same as df acting on del xi to give us the component functions times dxi, the coordinate basis covectors or covector fields. Now, by the result that we had already worked out earlier, differential of a function acting on a vector field is the same as a vector field acting on the function. So that's del xi acting on f. And del xi acting on f is what we abbreviate to this notation, del f del xi. Note that this formula should look exactly like the total differential on Rn. You must realize that the reason why we chose notations like del xi for coordinate basis vector fields and so on is simply to ensure that ultimately your equations will end up looking very familiar like the equations that you have for multivariable calculus, despite the fact that you are actually working on a manifold. Although I have said this several times before, I would still insist on reminding you that when you say del f del xi, you are not really taking the partial derivative of the function f with respect to xi. You simply can't. What you're doing is taking a genuine ith partial derivative of the proxy function f composite phi inverse with respect to the ith coordinate function. But since in practical situations we very often represent our functions not really as functions on the manifold, we actually represent them through proxy functions, this notation is something that we use directly in many cases. As long as you know what you're doing, things will be fine. Now, one big utility of expressions like this is that by inspecting the component functions, which are of course more familiar objects to us than covector fields, we can often decide on the nature of the covector field. For example, we can tell whether a covector field is smooth or not, whether it is really a differential form or not, by taking a look at the smoothness of these component functions. Remember, a covector field is defined to be smooth if whenever it acts on a smooth vector field, it produces a smooth function. So if alpha, a covector field, is smooth, then from the fact that del del xi's are known to be smooth vector fields, something we have already proven before, the alpha i's, which are the results of alpha acting on del del xi's, must be smooth functions. So if a vector field is smooth, all these component functions have to be smooth. Conversely, if all the alpha i's, I running from 1 to n, are smooth functions, then for any smooth vector field capital X can also be written down in terms of components, of the coordinate basis vectors. X can be written down as xi del del xi, and we had proven earlier that the criterion for X to be smooth is capital Xi's. All the component functions are smooth. Now what is alpha X? Alpha X is simply alpha I ddxi acting on X, which is xj del del xj. And here you can pull the capital Xj's, which are just functions, out of this. dxi goes and acts on del del xj directly, and that gives you a delta ij, as we have already seen before. And once you use this delta ij, which remember is a function delta ij, not really a number, it's a function, or it's a bunch of functions. If I is equal to j, it's a constant function 1. If I is not equal to j, it's a constant function 0. Anyway, ultimately what happens is you have alpha I xj delta ij, and using the simple property of delta ij, you can rewrite this as alpha I xi. Of course, sum over I being implied. Now note that if all the alphas are smooth, alpha i's, and the xi's are known to be smooth because capital X is a smooth vector field, then the action of alpha on X gives us alpha I xi, which is the sum of products of smooth functions. So alpha of X is bound to be a smooth function. Therefore, what we conclude is a covector field alpha given by alpha I dxi in this coordinate representation will belong to lambda 1m, that is, will be a smooth covector field or a differential form, or also known as a one form, if all the alpha i's are smooth functions, and only if all the alpha i's are smooth functions. Now, physicists are often more comfortable dealing with the components alpha I of a covector field, or the component numbers for a covector, rather than the actual covector itself. The covectors defined as linear maps from vectors to numbers, or covector fields essentially being linear maps from smooth vector fields to smooth functions, may seem to be a bit abstract to most physicists. Components are what we use all the time. And given the fact that these components are tied to coordinates, a natural question would arise: how would the components actually depend on the coordinates? If you change your coordinates, how would the components transform? In fact, in most physics introductory texts, covector fields and covectors are actually defined via the way they transform under coordinate transformations. What we want to show you now is that from our definition, the so-called defining transformation rule for covectors follow rather trivially. The question that we are asking ourselves is the following. You had a coordinate system u, phi, some chart, whose coordinate functions were given by x1 to xn, and now you have moved on to another chart u prime, phi prime, where u and phi prime have an overlap, and in the overlap region you have both x1, xn in force as well as x prime 1, x prime n, the new coordinates. And if you were to use a new coordinate basis and express alpha, the covector, as alpha prime j dx prime j, how would the alpha prime j's actually match or actually relate to the old components alpha I, where alpha I dxi is just an equivalent way of talking about alpha? Of course, both of these ways of talking about alpha can be used only in the intersection of the two domains u intersection u prime. Now, alpha prime I is something which is pretty simple. It's nothing but alpha, the covector field in this case, acting on del x prime I, the coordinate basis vector field in the new coordinate system. But alpha we already know is alpha j dxj. We are making that act on del x prime I, and alpha j's are functions. These are functions multiplying covector fields, and then you have added them together. So just by using the definition of how functions multiply covector fields and so on, you immediately get that this is the same as alpha j times del x prime I acting on xj, because this is nothing but dxj acting on del x prime I, but that we have already figured out is del x prime I acting on xj. This thing is changed into a shorthand which we use all the time. It's written del of xj del x prime I of alpha j. So basically what you are doing is taking the jth original coordinate, using the transition function to actually figure out what it would look like as a function of the new coordinates, and taking the ith partial derivative of that. So the general transformation rule for covector field components is alpha prime I is del xj del x prime I alpha j. Contrast this with what happens with vector field components. X prime I is del x prime I del xj xj. Once again, the coefficient for the transformation actually involves a derivative. It is the partial derivative corresponding to the jth original coordinate of the proxy function for the ith new coordinate. You can see that in a sense, covector components and vector components transform oppositely to each other under a coordinate transformation. I would also point out that this is exactly how you define covector fields in introductory physics texts, at least in first physics courses on tensors. But this definition actually follows trivially from the underlying basic definition of covector fields. We will meet differential 1 forms and their higher order cousins, the differential n forms, more and more often in the lectures to come. For the time being, let me point out one important thing. So far we have just talked about differentiation as something that can be extended from Rn to a general manifold by using a differential structure. Of course, the other half of calculus, integration, is something that we have not discussed so far, but it should be quite reasonable to expect that integration also can be done on manifolds. We will come back to this topic in some detail later, but for the time being, let me point out that differential 1 forms, as the notation suggests, do serve as integrands for line integrals. In fact, it will not come as a surprise to realize that differential 2 forms, 3 forms, etc. are basically integrands for what we call surface or volume integrals and so on. Now we will discuss this in some detail in the next lecture before we go on to talk about the higher order counterparts like tensors and n-forms. Bye till then.